All right, just a mic check again. Y'all can still hear me, correct?
Yes, we can hear you well.
All right. So I'm starting off with just addressing why we're doing this again. So basically, this is probably a lot for me and for people who still don't fully understand everything. I'm sure there's some veterans in here who have read all these papers and or read papers similar and probably won't be too impressed. But it was since I've been working with CNNs and MLPs and ResNets and LSTM for so long, I'd pretty much not learned a whole lot about transformers. So I basically picked a paper that was familiar enough for me to kind of get, and then built my way towards it. And also it turned out that VIT, which is from the Vision Images Worth 16 by 16 words paper that Eloy covered, is an encoder only transformer, and I used it on a problem that I think is similarly formatted as this paper, or as image captioning, whereas there's an image in a sequence, or you can consider it an image in a sequence. And I solved it with an encoder only, even though so basically I've solved it with an MLP and I've solved it with a CNN. And I didn't get a really good results with the LSTM, but the ways I solved it with MLPs and CNNs required like a very wide MLP that was like ridiculously wide. So it solved it, but it didn't like seem like it solved it well, in my opinion. And so I was just looking for better models, and I figured if transformers didn't work, I was probably gonna have to like basically go back to the drawing board. I'm not sure if I would have been able to find a model that would have worked. So the encoder only network working was a good sign for me, because basically it solved it in an extremely parallel fashion, which means that it's fast. And I figured that the decoder only adds sequential processing, which may allow you to make up for capacity with time, but I don't really know. At some point, we're going to talk about decoders, and I'm probably going to ask people in the audience what they know about the decoders, because I don't really know a lot about the decoder process. Another reason is because when I was looking into GLOM, like kind of hoping that Hinton maybe had made some progress on capsule networks, that essentially Hinton, like one of the first things he talked about was transformers and the query key value, and how it works well in the certain contexts. And I mean, I knew that transformers were probably one of the last things I would need to try. So I just started looking into transformers. So I started with Attention Is All You Need, and then the Vision Transformer paper, and then this. And Alex gave me an interesting paper to read that creates, it's like a transformer that creates meshes for things like 3D tables and stuff I would imagine you'd use in kind of like 3D modeling. So that seems pretty close to the problem we're trying to ultimately solve, which is like create a 3D surface of a brain. But I'm optimistic, because my simplistic VIT worked out of the box on the 2D problem. So maybe there'll be plenty of improvements on transformers that will allow me to solve the 3D problem. I believe, based on reviewing our previous discussion, oh yeah, so I watched the Eloy talk again, and I listened to the commentary after having learned some stuff, and figured maybe it was worth covering again, since I could contribute different things. And I kind of felt like some people, like I could tell Sergey had sort of he didn't seem as impressed with transformers as the world at large is. So it would be interesting to kind of hear his perspective on that. And it would just other people had some things that they said that I'm not going to comment on, but made me think that it would be worth talking about again. And finally, I'm interested in memory augmented networks because of neural Turing machines. You know, like how I imagine and think about neural networks has changed over time. So like I'm not sure I have any of my ways frames of thinking about them is correct, but the neural Turing machine things seem like they were trying to learn an algorithm, and by writing the memory and reading from memory in a way that a Turing machine would. And I think the thing that people want out of neural networks is that they generalize things outside of the training set or training distribution well. And I think to some degree, like if you're learning an algorithm, maybe that's possible. And I think at the same time, I have like a bias towards thinking there's like a little bit of magical thinking in there that maybe you can't learn something that's in your training set. But the way I think about neural networks now is that they're an attempt at like basically like in statistics you have biased estimators and unbiased estimators, and basically I would imagine that all neural networks are biased estimators of the training distribution, and basically different with different biases and different mechanisms of doing that estimation. And I don't know if that's useful or not, but it just it lends itself towards thinking that you're not going to learn something that's not in the training distribution. But that's how I think about them. If anybody can say no, of course neural networks can learn things not in the training distribution, please speak up, because I would love I'd love to learn something in that regard. But so background, attention is all you need. So basically this is like the original transformer paper, and to the right is the architecture. And so essentially there's an encoder and a decoder, and the encoder is composed of a stack of 6 identical layers. Each layer has 2 sublayers. The first is multi-head self-attention mechanism. I'm going to explain all of this stuff in subsequent slides in more detail, but I'm just going through the high level view here.
Yeah, thanks for that note, because I was wondering, like when I see this simple, clear picture, I'm trying to run away.
So do I. But so the first is a multi-held self-attention mechanism. The second is a simple position-wise fully connected feed-forward network. They employ residual connections around each of the 2 sublayers, followed by a layer normalization. That is, the output of each sublayer is layer norm of like what came before plus whatever transformation you've made. And the encoder is similarly structured with multi-headed attention followed by feed-forward layer and linear layer and self-max. This slide probably doesn't add that much value. It starts kind of letting paint dry. So the background on attention. I think I probably should have put this first, but I think the most important thing is the query, key, and value discussion, or at least for me. Like the thing I didn't understand about transformers is basically I didn't understand the attention in this context, self-attention. So basically, like if you have an image input, you the query is sort of like the signal. Like if you're like a robot and you're an observer, like the query is like the thing that you've observed that should like stimulate change of state within your network. So like if you're doing image captioning, that will be in a lot of it will either be the image or the words that you've generated thus far. So so basically you have this input that you do a linear transformation on, and you get a query. And you also take the input and you do a linear transformation on it with this key matrix. So basically what this ends up doing is you're comparing projections pairwise of like the input with other parts of the input. So there's like, it seems like the way I've heard it described is there's pairwise similarities determine the amplitudes of the softmax, which basically attenuates the value matrix. So there's another linear projection of the value of the input to create the value matrix, and you basically amplify or attenuate various parts of that linear projection based on this equation here. So what the multi-headed attention, basically you allow multiple heads, and each of these heads creates different linear projections of the input based on the input itself. And based on other things that I've read that are in this presentation, you'll see that some of the heads will be learning local relationships, which is like things that are close together will have a greater effect on the final result than things that are far apart. But some heads will learn global attention, and I think the chief advantage of attention transformers over convolutional nets is that convolutional nets don't have access to a global field unless you stack many layers of convolutions on top of each other and grow from local to global in such a way that the receptive field is global. So you in a shorter path from input to output, you have a receptive field that is larger, and that depends based on whether having a global field is good, because backpropagation is involved. If a global receptive field isn't useful, then my guess is the heads wouldn't learn to view global things. But so basically you're looking at pairwise relationships and then growing those relationships with depth. So the next layer will be taking the pairwise relationships learned in the previous layer and like creating like sets of another pair of pairs, and you basically create filters of varying complexity based on how your transformer is. So I've described the query key value aspect of transformers. I've described the self-attention mechanism and the multi-head. The multi-headed.
Can you, William? Can you pause just for a second and ask a question to at least people who are on the call? Like, is the explanation of how the attention works clear? And if the explanation of the encoder part of the transformer crystal clear, very easy, all of the aspects are clear?
Yeah. If anybody has questions, please ask them.
I feel like you.
And not just of me, I mean, like of the group. There's a good chance I might not know them, but somebody can probably answer the question.
Yeah, like since we're doing a discussion also, I'm just like this transformer thing widget is much simpler than even this illustrated transformer is describing. And like, as you said in the beginning, that first you thought some kind of a magical things about neural networks. So the transformer still feels magical even after those explanations. So if anyone on the call, the transformer or in the room, the transformer feels magical, let me know, because like there's it's not magical, and the key there is parameter tying. Parameter tying, the same as we do in convolutional neural networks and things like that. So I don't know if that came through and came clear that we're using a bilinear transform, the same bilinear transform for each location in the input. And that's parameter tying. The bilinear transform, call it key, value, query, whatever, but it's a low rank bilinear transform. And then we're normalizing with softmax for bilinear transform so that we can average the input according to these parameters and create the output of the attention. But then once the attention output for each, unfortunately, I need a whiteboard to be clear, for each of the locations, input locations is created, we use a feed-forward network, which is also parameter type. For each of the location, you use the same feed-forward network, MLB. And then again, you apply a bilinear transform and reweight everything. So the key, as I see, the mathematical key is parameter type. Sequence length repetition of the same bilinear transform and sequence length repetition of the same feed-forward network. And that's, you do it one after another. And there are other things which kind of didn't come through at me, at least in the original transformer, is skip connections. Every attention layer followed by feed-forward network is augmented by a skip connection. You add the input to the output. So you represent each token or each embedding of your input as a weighted combination of all of the other inputs, and the weights are obtained by bilinear transform. So X times A times Y. So X transpose times A times Y. And where is X is your key, I guess, and Y is your query or any other token. I don't know. I feel like drawing on a whiteboard would be much better, but I don't know. Let me know if you have a clear idea.
I think I understand it, but I can't draw a very simple diagram of it like you quip a lot. So
I think it is possible, right? So like what I'm talking about is we have X, that is your embedding, original embedding. It's not always working as it. The embedding, yeah, if you can keep it here, William. So we have a sequence of words. Vectors, right? They're represented as the same dimension vectors. X, Y, Z, whatever, W. So what is happening here? You compute X transpose, say, X transpose AY, and then you compute X transpose AZ, and then you compute blah, blah, blah for each of them. Oh, AZ, AY, X, AW. And then you take Y and you compute, well, you get locations, X transpose, and you also compute X transpose AX. So there are 4 elements in the sequence, and you sort of get 4 elements in this bilinear transform for X. You take Y on the left and you do the same for Y. You take Z on the left and you do the same for Z. And so for each location here, you get a number. Apply softmax to this number and you got the weights. That's how you add up those vectors together with the weights. So I need to be able to write better, but let's spell it out. So you get 4 weights. That's what transformer is doing. A is the parameter, the same parameters. You learn A. It consists of WQ and WK. It's low rank, but it's a combination of projection matrices, but it's still this A, and that's what we're learning. Once you obtain and normalize those weights with softmax, now instead of actually normalizing, adding weighted, let's call those alphas. You have alpha X, you have alpha Y, and this sub-coefficient is what happens here on the Y side. So you have all of this alpha Z and alpha W. But instead of doing it, you're applying another projection. You're averaging projected versions of those matrices. So if you put all of that together in a formula, then you get softmax of your X here times your WQ, following the notation on the left, times WK transpose, X transpose, and go with the square root of T or whatever. But that's how you get the weights. But this is nothing but what I just described. And the key is parameter time. It's sort of you pass your system through the same transform, your relative transform. But once you got new values with I forgot if you are transposing or not. Sorry about that. It's probably WV transpose or maybe just WV. It depends. Make sure the transposes are correct here, so parameters match. But once you do this, you get new values of X, new values of Y, new values of Z, and W, which are mixtures of the previous values. And you apply the same MLP to those values, and then you do a skip connection. You add what you had before to what you just got, and you repeat that many times. The same thing with multi-attention heads. But like when I first heard it and looked at it, I was super confused, just following William's style of discussion, because I couldn't also see like what's going on behind this linear algebra. But now I think it is parameter time, because you keep repeating the same model. And I mean, it's powerful. And as Alex pointed out, and as we found out, this model could be just an MLP as well, with some certain mixture, parameter time and mixture of all of the inputs, and continuous sort of mixture. That's my guess, of course. This is not, but that's what I see from the math, from the linear algebra. Okay, sorry, William. I thought it's worth interjecting.
Could I ask a question real quick? So maybe I missed this, but what is the queries, keys, and values? Is this like one language and then the keys are a different language?
No. Look at this. Look at what I just have on. I don't know if you can see my mouse or how it's.
They're just so the weights are just differently randomly initialized weights. X is the same input sequence, so you have query key and value are again the same input really. It's just, and you have weights, you just tie them differently and do self-attention. By self-attention, we mean dot product scaling.
I see. So they literally just take the same input and then they just have 3 different
Projections.
Projections, yeah.
3 different projections, yes.
Okay, see, like the thing that I find a little confusing about this is it just feels like they're just kind of doing a hodgepodge of things. They're like, okay, we're going to do a little bit of global attention, a little bit of local attention. We're going to do some skip. We're going to do that. Is that, it just feels so constructed.
Well, I actually think it's a very simple
like they've combined
idea. Sorry, go ahead. No.
But go ahead, Kevin.
I actually think it's a very simple idea that they just like put on a whole bunch of other things into, in that they said, okay, scaled, scaled dot products. Dot products are powerful if you feed them into MLPs, if we scale them correctly, because we think that that's a good mechanism. And then we'll go and say like, what's the sequence length? We'll go and see like skip connections are good or bad. But I think the central idea of this was just like, let's scale dot products for a sequence and see whether that like really works.
I think bilinear product is the key. That like in order, so before attention in Badenau's paper and follow-up papers was some neural network that learns to predict a weight. And here what they're doing is, well, let's learn a bilinear combination of X and Y. Let's learn A for the weight, because that's all it does, it gives you the weight. Like which weight between X and Y, relative weight. And if you look at the original Badenau paper, you took something like a reference point and a state together as an input to the network, and a feed-forward network predicted the weight. Here, let's the weight be the bilinear combination of that reference X and whatever else. I think that is the key, not the projection, not anything. It's the bilinear combination to predict the weight, and it's the same bilinear combination. Of course, it is not symmetric. Left and right is different, and A is not a symmetric matrix. Well, yeah, it is not a symmetric matrix. So that's why those positions matter. And again, parameter tying that lets us learn it quickly.
All right.
Okay, yeah, I think we can just continue.
Yeah, so I'll say like I'm gonna add something that's hopefully doesn't confuse much, but like I'm gonna work back from something that I thought originally that wasn't true, and maybe Sergey can comment on how it's close or far away. But so like my original thoughts on what attention was that like basically like if you took away this WV, then no wait. So basically I thought that like you were taking the output of this softmax and then multiplying it times X, and then that was the output of the layer. But and for some reason that like basically you would have just had like some sort of linear projection of X in that regard, but you're basically like having a linear projection of a linear projection here. Like I don't know if that's probably just too confusing, but anyway, I'm gonna know.
It is just a linear projection, yeah. Like so, instead of averaging directly the tokens, you're learning in which space they're better be averaged, and that's W superscript V.
Okay.
I think the key is learnability of those projections, that you're not like choosing them. It's like depending on your task, the model is free to choose which space to project.
Yeah, and one thing that I mean, you might not think about if you haven't worked with them, but like if you add heads, like as you add heads, that allows like you to have variety of these different projections. Just like in convolutions, having a variety of filters can improve results. Like having a variety of heads allows you to have different projections of your input, which allows.
I think the heads was they mostly added the heads because it didn't train well when they just did one head.
You ruined it.
I don't think that the number of heads is too deep. It was just that it wouldn't learn with just one head, because then it would have to be right immediately in terms of learning it. And then they added like 8 and they were like, oh, now it does work. And you can actually remove 7 heads after training for each of the things, and it still works almost exactly the same way. There's actually a lot of papers on just like removing heads during training because they're not needed, but you need the number of heads just to make it work.
Yeah, this is like ensembling ?
Yeah, exactly. Ensembling, but then one of the heads becomes 99% of the ensemble, basically.
Is that what's observed in practice?
Yeah, there's a lot of papers where they just remove heads during training because it actually works better, but they just need the initialization of 8 heads so they can learn a path from one of those 8 heads. And you just increase the probability that the path is going to be learned if you have more heads. That's basically what they say. Like if it doesn't work, just add a little more heads. And there's a lot of papers on just removing heads during training as well. Because then all of a sudden you have it's like L1 regularization. There's a lot of weights that are not used, for example, in an MLP or for convolutions. And in this case, it's mostly heads that are not used for transformers.
That's interesting.
Do you think that, so, and I know that this is like derailing the conversation.
Please do.
Do you think that the time, well, basically a head is a single MLP with the attention specified for the MLP, right? Do you think that the MLP choice is the right thing, basically?
No, there's no, a head is just self-attention.
Right,
This is
right.
bilinear transform. There is no MLB yet. It's just
Okay.
that thing that we just described.
Okay, so you can have multiple heads for a single MLP that goes through.
Yes.
Yeah.
Okay, never mind then. That's not a good question.
Actually, I think they average or something for the heads.
Mhm.
And because you're average.
They project. They can
Right.
calculate and project.
Yeah, true.
Yeah.
But so if the weights in one of them becomes very low, basically it's not needed anymore.
Which is a weighted average, by the way. I take that back. Linear algebra.
Yeah.
To do it in my head.
And what happens is that a lot of the heads will have very little, very small weights. Basically, that's what happens. And then you can remove them. It's the same as like filters removed from a convolutional neural network. There's like 4 or 5, there's a lot of filters that are not needed in general. So when they look at like making it smaller, especially because transformers can be super, super big, they can mostly just remove a ton of heads, like 80% or 90% of the heads, without sometimes gaining accuracy and sometimes just staying the same. I was pretty surprised too, but yeah. I was actually reading the first paper, the thing is all you need. And I think they even mentioned that they just added heads.
You need to talk to Ria side after the meeting.
Okay, yeah.
I was thinking the same.
They just added heads because it just worked better. There weren't even it wasn't like a very we're gonna add more heads because it makes sense, but they just did multi-headed attention because they said it trains better.
Well, I mean,
No, I know.
Is it a bad?
True, but then afterwards, people found out that actually most of the sort of information goes through just 1 or 2 heads per.
Well, this is back to the lottery ticket.
Yeah, it's exactly that. They basically improve the chances that the lottery ticket will be reached. That's basically it.
So we just should do ensemble
Right.
and
Yeah.
then choose the model that works in the ensemble.
Distillation learning.
So after you get this output from the heads, from the multi-heads, there's just there's this position-wise feed-forward network. It looks like there's 2 affine transformations on it, on the heads after each layer. Is that right?
Well, that looks like a 2-layer MLP with a ReLU activation to me.
Okay, maybe that's probably not part of the. I don't know. So embeddings and softmax. So basically, when you're working with natural language processing, you need an embedding representation of the word. And you convert back and forth between embeddings and words. The softmax is used to basically represent which word in the dictionary is represented by the embedding once converted to hot representation. The positional encoding, essentially, because there's all these pairwise dot products, it doesn't have the inductive bias that the CNN has, where it's like scanning left to right, and then that scan is preserved when you go to the next level. So they use these positional encodings where they add some representation of what part of the sequence the input is to the input in order to go to the next stage. It allows it to know parts that are near in the sequence are related more than parts that are far away, or pixels that are closer close and pixels that are far away are far away. It says that you can either have a learned or fixed representation of this. I'd be interested to see like learned positional encodings and how they change based on problems or if they change. But I don't know about that. So this is probably hopefully somebody can say some of this information is wrong, but the one thing that I took away from this is that self-addition has the shortest path length from input to output. And if you're kind of conjecturing that gradients do better when they have shorter paths, they propagate more efficiently when they have shorter paths, then that would be an advantage in self-attention. Recurrence, I don't think it's too controversial to say that like backpropagation through time has limitations. So if you have things that are far away in time, then recurrence has a kind of a cap on how useful with an LSTM. Convolutions, their path lengths determined by the number of filters, I believe, or the sequence length, sorry. But anyway, did anybody get anything out of the attention's all you need that is represented in this table that they would like to add?
I may want to add that complexity per layer is much lower for newer sort of attention methods. I think they go towards like O n log n or something, or even smaller, like O(n). But that's not the original self-attention paper. It's like linear attention or whatever. There's like a bunch of people that were like, oh, n squared d is way too much. We need to go smaller, and they did. But yeah.
Yeah, and I know the paper you covered with VIT with the pictures worth 16 by 16 words. What they were doing there was that, like, if you had a 256 by 256 image, you would break it up into patches and create embeddings from 16 by 16 patches, and then add the positional encoding to those patches that represented like the 16 by 16 subset of that image, and that decreased complexity. I don't know by how much, but that's one of the reasons I chose to start with VIT, was because basically I saw people complain about the original transformer being the complexity being too high, and that at least reduced it by the number of patches to some extent by grouping them together. But I don't know too much about how else it's been, the complexity has been improved. So this is finally getting to the paper that we were supposed to be covering. That was all background. So basically, in this paper, they have several contributions, one of which because Alex mentioned this, but I kind of agreed with him when she pointed it out, that like the memory is probably not all that useful. It might just be, in fact, increasing the capacity of the network and not any sort of doing anything that it's claiming. When you look at the results section, when they do the ablation study on the memory, it doesn't look like the relative change is that significant. There's always some change in the benchmarks, but it's not much. I would guess that the contribution, if they have any, was their the meshing. So what the meshed cross detention does is basically the decoder used in the original transformer only looks at the final output layer of the encoder. Their decoder, each layer of the decoder looks at every layer of the encoder rather than only the final layer of the encoder. And they do some things where there's a data set on image captioning where they have some captions that weren't in the training set, and there's a data set that's that specializes on that phenomenon that they test on, and they do well. But I'm not going to go too much into that. So here is the overview of the mesh memory transformers. So essentially, so you have the query key and value that we discussed earlier, and then you have the attention, and then this is basically like a layer, like a single encoding layer. What they've done is they added they concatenate memory onto the key multiplication and the value multiplication while leaving the query unchanged. And they claim that that allows that a priori knowledge to be inserted into the translation. So a priori knowledge is like if you see a basketball and you see a person, you might not have enough. Can y'all hear me? I just heard something. Yeah. So basically, the a priori knowledge would be like if you have a basketball game going on, but you only have like a basketball and a person in the image, you might not have enough information to know that it's a basketball game, so your caption might not reflect it. They're asserting that this memory structure allows them to know more information. And I got excited mainly based, I mean, like I didn't know if I quickly whether this paper would be as robust as I would like it. And I was at the time only working on a two-dimensional problem, so image captioning was of interest to me. What would have been really of interest to me, like now that I'm working on 3D, is to see like a memory structure that was useful in video captioning, where like something they've done on a single frame is remembered for processing of future frames. That would have been like actually of interest to me and probably useful in the long term. But this memory structure is probably just increased in capacity because it's not conditioned on anything new. It's just like learned during training. So anything new meaning like there's no like previous frame information being fed into this frame because it's an image caption. So I don't really know how they call it, why it's called memory. See anything compelling to indicate that it's anything more than a larger, an extra matrix. So now the other contribution is keep seeing Slack messages, sorry. The decoder layer in the original transformer, like all these, like it looks fully connected between the decoder and the encoder. There's a really one-way relationships. The encoder doesn't know about the decoder, but the decoder knows about every layer of the encoder's output. So every layer of the decoder sees all of these layers. And I guess that would be like if you were doing a convolutional network, if you had a decoder that looked at the output of each layer of a convolutional network rather than just the final layers feature extraction or something like that. I don't think it's should. I would guess that most of their performance came from this, so you can look at lower level relationships and higher level relationships, and perhaps have extra layers that don't matter that much, and not suffer too greatly from having extra layers because of these essentially path shortcuts for the gradient. So I mean, the rest of the slides is just me going through the math of that. So that's the high level phenomenon. We kind of talked about all of this. So essentially, so like you have the query key and value equation for attention. Now you have a concatenated memory, a learned matrix for the memory, and a learned for both the key and value. So, and all of the rest of the downstream. That's for each layer, and so each layer has these memory values associated with the keys and values and their self-attention equations. And then you have the feed forward network after multi-headed attention that was standard in transformers. It's not new. And this is the full notation for basically the encoder. So you have this multi-headed attention with, and then you have these add norm basically just means there's a residual connection here and batch normalization. And then you take the results of the multi-headed attention and you run it through the feed-forward network. And each of these steps has residual connection and batch normalization. The decoder, I find this part of the image to be not particularly helpful, but so the x1 to the x tilde 1 to x tilde n that's basically the output of the encoder heads. And basically this whole image is saying that you take these values, you learn this gate of like whether or not the bilinear projections are useful at each stage, and then you sum them up, and basically attention is it's the same thing, except for you have a weighted sum. So that's gated. So you start here, you have this is the query. So the query for the decoder is not the image pixels. The query for the decoder is the captions. So you have the captions basically determine like how each step of the decoder changes. So every step of the decoder you have a new word, and then you have like each of these XIs. So for each layer you take the caption and you do the self-attention step, and then you take the self-attention and you use that information to, along with the inputted the captions, in order to learn a sigmoid of this input. So it's the same cardinality as the self-attention output from the previous layer, but you attenuate between 0 and 1. So, and then you take these alpha coefficients and multiplying by the self-attention for each of the layers, and then you sum them together to get the decoder's layers output. So basically the sum represents, like you're doing self-attention at each stage. You don't know whether or not it's important, and the alpha value tells you whether or not to look at each layer. And then basically each layer is gated, and you sum all of the self-attention results from each layer, and you get the result. One thing I found that was not very clear in this paper was how each decoder layer looks at the layer above it. So it's not as far as I can tell, it's not in any of the equations of the paper. But clearly you would think that each decoder layer is dependent on the previous layer. But what the paper focuses on is how the decoder layer each layer is dependent on all of the layers in the encoder summed up, as is mentioned here. But what I would have liked to have seen is how that combined with how it depends on the previous layer of the decoder. So I feel like it's incomplete. My guess is that if you understand transformers, that would have been self-explanatory to the reviewer, but I didn't understand that in this paper. Okay, so basically I had some questions that I wanted to ask the group, and if y'all have any questions about the previous page, please ask them. I'm sure that wasn't a great explanation, but it was as clear as I knew how to be.
I have a question. Did
Yep.
you cover positional encoding?
I briefly mentioned it, and it's a slide, but I didn't like show any examples.
My question is why they use both sine and cosine.
Oh, that's a good question, and I don't know the answer to that.
Because
So-
it works really well.
Yeah,
I know, but think about what we're gonna do, right? Why we're using it. Like, what's the goal? We could have just numbered each input with additional dimension, 1, 2, 3, 4, 5, whatever. But the goal is to give, because we're in the, sorry, I just had to, in the graphical neural networks, in this graph convolutional neural networks, we need the permutation invariant mean, we're averaging. So because we're averaging, we're losing the information. And so, okay, that's the goal of the, let's add that information.
It's also cheaper. If you have a long sequence,
Yeah.
you can just go take sine, cosine. And if you take both,
Even and odd.
if you take both at the same time, it's like a unique key, basically.
That's the point, right? It makes it more unique between even and odd.
Yeah.
Well, we need a dense representation of location that is unique.
Okay.
Like we can't do sparse 1, 2, 3, 4, 5 because neural
Right.
networks.
Or
right,
one hot encoding.
Yeah, they're not good with that. So we need to give them dense representation. There's additional information that kind of encodes. So whatever works. I mean, you can use any other additional.
Yeah, I think they did a paper on looking at what works the best, and it turned out sine cosine works the best. Because
So they
it's,
did try other.
no, not this paper specifically, but I think there was a paper for transformers that looked at positional encodings and like what kind of works better.
Do you
I
know-
think it's because it's the most unique, because if you take sine, it's gonna be very, like, if you have a very long sequence, like 1,000, the numbers between the two sort of points are gonna be very similar. And
Oh, yeah, and I think they've mentioned in
Sine
one
and
of the
cosine,
papers,
it makes them.
it makes them more dissimilar.
unique.
I think they mentioned in one of the papers that one of the reasons they use signed is because like they wanted to work for longer sequences than what they trained on. And since signed is periodic, they were kind of hoping that like the periodicity of the positional encoding would allow it to generalize the longer sequences or something like that.
Yeah, that too.
But I'm sorry I interrupted you.
Oh, thank you.
So I had some questions, I think. Okay. All right. Is it true that the encoder output for a single image at inference time should always be the same since it's not conditioned on y less than t? So basically, this is image captioning. So a single frame is like one image. So it seems to me that because of that, and because the encoder is not conditioned on the caption, that the encoder is basically a feature extractor, essentially. Like you're only going to get one representation out of the image at inference time. Like, correct? I don't know if that question makes sense. So like basically the decoder is outputting a single word each pass through, correct? So like it seems like they're basically re-implementing recurrence with the decoder, even though they kind of took away recurrence to some degree. Does it so it seems like you have to step through the decoder multiple times per image, but it doesn't seem like you would have to step through the encoder more than once because the encoder is operating on the image. The encoder is basically like creating a representation of the image for the decoder. So can anybody like say whether or not that's a true statement? I don't know. Because that's like really important to my understanding of transformers, basically, is like the decoder is basically dependent on previous time steps, right? Hello?
I don't think that the decoder is dependent on previous time steps, given that it's not like. Sorry, this is not a LSTM or anything else in that.
Yeah,
sense.
like where does the time come
Yeah, this is simply like you've
they're
put stuff
generating
into feed-forward
captions.
networks.
They're generating captions, right? And as far as I understand it, they're generating captions one word at a time. And then that every new word is fed through the decoder as new stimulus for the decoder to generate the newest word. I mean, maybe I'm wrong, but that sounded like recurrence to me.
No, they must generate it all at once because GPT-3 is a transformer, right?
Right.
Yeah, on my way here, I was just listening to a podcast, about his name, the open AI guy about codecs. And he's like, yeah, the problem with this code generation, it generates it all at once. It doesn't have a chance to go back to is it correct or anything. So it's just all at once. That's why you put the sequence length 2000, blah, 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 or something.
Okay. Well, if GPT is an encoder only transformer, that would make sense to me. But if GPT,
No, it's a encoder decoder.
okay,
Yeah, but it doesn't matter, right? Decoder is just the same
It's-
feed-forward process.
Yeah, it still goes through a feed-forward network.
What they can do is like, for example, with GPT-3, if you're trying to generate a lot of language, you generate 2000 words, then you take those 2000 words, put it back in the encoder and then generate the next 2000 words. But that's different, I feel like, right? I mean, if it wants to keep generating text, for example, those articles that it generated, I'm pretty sure what they do is just take the output that they just generated and input it to itself, and then it keeps talking. But like,
Yeah,
that's a
I
little
think that's
different.
not his question
Yeah.
specifically, but yeah, I agree.
okay. Well, I still need to find a way to get the decoder into my brain. Apparently, I missed how it is able to be fully parallel.
Doesn't the decoder, so if the encoder has parameter sets for n time steps or whatever, doesn't the decoder also have parameter sets for n time steps? Isn't that how it works?
I thought so.
Generally,
That's
it does,
what I
yeah.
So the two things happen together. You have this huge multiplication for the whole sequence on the encoder, and then the decoder takes that whole thing and decodes that. Right?
Okay, so basically the positional encoding is kind of used on the decoder to simulate the recurrence, I think. Would that be another way of saying it?
I mean,
But there's no recurrence.
no, I don't think so.
No,
But
it's-
one thing-
yeah, to simulate it.
It's just that the input sequence is of the same length essentially, because it has to attend to this
Yes.
sequence.
Yeah, that's what I see as well, yeah. Well, any more questions, or we can stop the recording here? Thank you, William.
Okay, sorry, whatever. Yeah, none of this